So another example of being able to use the critical value method to be able to apply the derivative is in the shortest distance type of problem. So we have a plane, 2x minus y plus z equals 1, and we want to find whatever point on that plane is closest to the point -4, 1, 3. All right, so this is actually a problem that we did earlier in the course where we just did it with a formula. Let's see how we can utilize a derivative to be able to figure this out. All right, so first thing we want to do is we want to figure out what the preliminary equation is. And the preliminary equation is going to be kind of sneaky. All right. But we also need a secondary equation. And the good news is the secondary equation is given to us right away. All right, so we can rewrite that as z equals 1 plus y minus 2x. What are we trying to optimize? Well, we're trying to find the closest point, all right? And that means that we're trying to optimize the distance. And we know that the shortest distance to any point is a straight line. And so remember earlier in the course that we looked at the distance formula. And so our distance d, as you might recall, is going to be equal to the square root of x sub 2 minus x sub 1 square plus y sub 2 minus y sub 1 square plus z sub 2 minus z sub 1 square. And in this case, we already have the terminal points, or the initial point, -4, 1, 3. And x2, y2, and z2 are unknowns. They're points that are on the plane. So what we can do is we can rewrite d as x plus 4 square, so minus a minus 4, plus y minus 1 square, plus z minus 3 square. All right. Now, we already know that z is equal to 1 plus y minus 2x, so we can substitute that back in and make things a little bit easier for us. Instead of being in 3 variables, we can be in 2 variables. So that's going to be x plus 4 square plus y minus 1 square plus, now if we substitute, we have 1 minus 3, so that's going to be a -2. So we're going to get y minus 2x minus 2 square. All right, so that's the function that we're trying to optimize. All right. Unfortunately, being able to find the derivative and then finding the critical values of that might be rigorous. Not impossible, but fairly rigorous. To ease that on us, what we can do is we consider the square of the distance, right? And justify to yourself, but the points that optimize the square of the distance, so in other words, that optimize d square, also optimize d. And clearly, if we got rid of this radical, our lives would be much easier with respect to the derivative. All right, so we wouldn't have a chain inside of a chain and then a 1/2 power and all that stuff. It would be really easy for us. Right? And justify that to yourself. If you have a point somewhere in space, I'm going to call this, and we have the distance d. All right, so let's call that our distance d, and this is some point P, and this is the point that we're actually looking for on the plane Q. Well, what if we squared d? Well, it would just look like this. So it would basically be the length times the length. And no matter what, the length times the length is going to be smaller than any other lengths. All right, so if we did this, all right, whatever that arc might be, and let's call that a, and then a squared might look something like that if we multiplied those together, or not say double the distance, but squared the distance. Well, no matter what, the shortest distance squared is going to be shorter than any other distance squared. All right, so try to justify that for yourself, all right, just to make sure that you do understand that it is legal to do this, but more importantly, it's going to make our lives a lot easier. All right, so knowing that, then what we can do now is we can say that d squared is going to be equal to x plus 4 squared plus y minus 1 squared plus y minus 2x minus 2 squared. And now it's much easier to find dx and dy. In fact, we're going to find d2x, which is going to be 2x plus 4. This one doesn't matter because there's no x's, plus 2y minus 2x minus 2 times the derivative of that 2x inside, which is minus 2. That's going to be equal to 0. And so we can rewrite this by doing some distribution and collection. So if you'll verify this for me, we're going to have 2 times negative 2 times negative 2, which is 8x's and 2x's, so we get 10x. We get 2 y's. And then finally we get 8, and we get 8, which is going to be 16. So we can just say equals negative 16. All right. Now, we need d sub y, or do we need d squared of y? All right, that should be pretty easy. This term doesn't matter because it has an x in it. Well, it doesn't have any y's in it, excuse me. So we get 2y minus 1 plus 2y minus 2x minus 2. And that's going to be equal to 0. Similar to before, if we collect like terms, we have 2y and 2y, which is 4y. We have a negative 4x. Right? And then finally, we're going to end up with, I'll come back to it. And then finally, we're going to have negative 2 and negative 4, which is negative 6 equals 0. I did notice a boo-boo up here. Right? This should be negative 4y. I forgot to multiply by the negative 2. So all I did was I just did 2y there. All right. And so we could rewrite this as 4x, negative 4x plus 4y equals 6. And what do we have? Well, we have a system of equations. And this system is going to be really nice for us. Okay? So we have 10x minus 4y equals minus 16. And then we have negative 4x plus 4y is going to be equal to 6. And now we can see how nice and easy this is. So we're going to end up with 6x equals negative 10, or x equals negative 5/3. We're going to back substitute. We're going to solve for y. So we could just plug it in right here. So we have negative 4 times negative 5/3 plus 4y equals 6. This is just going to come into 20/3, and we're going to add that to both sides. So 4y is going to be equal to 6 plus 20/3. So, and that's going to give us 38/3. And if we divide by 4, that should be 19/6, but let me just verify that. Just being lazy using the calculator. So y is going to be our 19/6. Oops, no, I made an error again. Oh boy, not good. All right, so this is a positive 20/3. So it would be 4y is going to be equal to 6 minus 20 over 3. All right, that's going to be 2/3. All right, negative 2/3. And so that means that if we divide by 4, y is going to be equal to negative 1/6. Hopefully. And then finally, remember z, all the way back in the beginning, z was equal to 1 plus y minus 2x. And so that means that z is going to be equal to 1 minus a sixth minus 2 times negative 5/3. And let's see if I can compute that without making another error. And I'll end up with 25/6. All right, now we are going to do this problem again in the next section using a different method. So hold on to these answers, all right, as well as hold on to the previous answer, so that way we can see that there is a secondary way to be able to attack these types of problems. All right, so the next video is going to show one more application of a volume, and it is going to be pretty algebraically rigorous, so brace yourself, I suppose.